Thank you for the invitation. It's always a great pleasure to visit this wonderful place in Marseille. Also, it's something like some comeback to the foliation group, because I have been working in foliation many times and now not so more. Okay. So, as everybody noticed, in particular the one in the session of problem, because it has been done, the three persons in these are John Mather, which is important in particular for the group of homeomorphism, diffeomorphism, and so on. Bill Thurston, and André Flieger. And André Flieger passed away 1 year and something ago. Let me say some word about foliations. And so I wanted to make a joke, but when you make a joke, it has to be a little bit serious. So let's make the serious joke. And you will see it very cultural and has something to do with the centre, with Beaubourg, the Centre Georges Pompidou in France, in Paris. There. Okay, so foliation, people think that foliation, more or less, the father of foliations are, the three fathers are Charles Mann, essentially, but also George Reb and André Flieger. And I have seen a paper by André telling that, no, the beginning of foliation theory is a paper by Ereshman and Reb in 1944. Oh, that is the paper creating the theory of foliations. But in the other paper of André, he says that, yes, but the question about the existence of foliation on S3 comes from Hopf in 1935. So in 1935, the word foliation did not exist, so it was not a word in foliation, but he asked is, on the sphere S3, there was some planes transverse to some smooth vector field, and that this plane has the integrability condition, that is our foliation. And then there are two different answers, let's say. The first answer was certainly a surprise at this time, is that yes, there exists foliation on S3, and that has been done by Reb, a student of Ereshman, and by this wonderful picture. And this picture is indeed very simple, but nevertheless, many times people have difficulty to figure it. And so there are many talks starting with explaining what is a Reb component. And so in 1968, Bourbaki asked to André to make an exposition of Novikov's result about the existence of Reb component. And so he drew this picture, and in the audience there was, I was not there at this time because I'm not so old, but in the audience there was one of the famous French mathematicians, Adrien Douady. And at some moment when André is very kind, very pleasant, but he's also serious. He don't make jokes, and in particular not bad jokes. That was not at all the style of André, but Adrien, yes, made bad jokes, and many bad jokes. And so when André just looking on the other side, he just goes there, and wrote, not exactly this one, but because this one is done by Marcel Duchamp, in fact in the same year. So that is truly cultural reference, let's say, some piece of art. I will write so that people can write, can understand, but only French people will understand. And if I translate in English, I guess I will have troubles with the community. So it's written. So as I tell you, it's a piece of art by a famous painter, Marcel Duchamp. It's nothing else. L'aspirant habite Javel. I knew this story, but I didn't know what is Javel. And so Javel is a place in Paris in the 14. Okay, the French understanding what is written there, tell to their neighbor, the other will understand someday. But anyway, it's a very not politically correct. You have to change the order of the things for making a bad joke. And André hated that, so sorry, André. You don't, okay, sorry. William Thurston in this theory of foliation has been some kind of bomb. And I arrived after, sorry for Japanese people, I arrived after Hiroshima. So Hiroshima Thurston mostly makes that the community of people working on foliation almost disappear in France at least. That is, before, the question was, what manifold admit a foliation? Can we classify foliation? Is it possible to make foliation with such or such property? On that, arrives Thurston and say, yes, take a plane field anyway, you can make a small perturbation, look at some characteristic class, and if we, yes, make this surgery and so on, and you get your foliation, and does that. Okay, so people was a little bit, I don't know if it is, it's a wonderful work, but it makes that all they was trying to do has no more meaning. And in fact, I arrived in foliation theory after that. So in the 80s, Rosenberg made me some question, and that was my first contact with André. So in 83, 84, in France, there was no position at all. There was very few positions at CNRS and so on. The situation was complicated. Poenaru asked me if I want to make a thesis in mathematics, and he tell me, in that case, you will have never position at all, no possibility. Okay. So that was the difficult things. But anyway, I get my first result, and Rosenberg asked me to speak with André Flieger, who is visiting for a short time IHS. And so I take my phone. For me, Flieger was some kind of god, or I don't know, the reference. It was two papers, one about, you make the title in English, I'm not able to do that, to cohomologie à valeur dans un faisceau de groupoïdes. So, and the other was variété feuilletée, which is much easier to read. And so I was calling, I don't know for you what is the reference like that, but for me it was like that. But at the end of the phone call, we were already telling tu. And I was calling him André after just 1 minute at the phone. So I was then going to IHS and explaining my result, and very afraid indeed. And André rapidly tell me, oh, that's complicated what you are doing. Oh, that's so wonderful. But can you explain again? Because I did not understand exactly. Repeat a little. And I was so surprised that this so big person was so accessible, so kind with me. Okay. And so after that, when I did not have any position, because there was no position, at some day I received a call from André, who didn't know me so much, but just Rosenberg told him that I was in trouble. And so André called me for telling, yes, I found something for you in Geneva. And so I spent 6 months in Geneva with him. And it was really wonderful. Okay, let's speak a little bit on math. On his math, I already told that. So I guess that's some result of André, which is now very useful for people working with foliation codimension. One in particular for pseudo-Anosov flows is this result that I already mentioned during the course of Katie, is that if you have a codimension 1 foliation, and if you have some transverse closed curve which is homotopic to 0, then there is a leaf having whose holonomy is trivial on one side and not trivial on the other side. With that, he gave a different answer to Hopf's question. So Hopf was asking if there was foliation on N3, and George Reb told, yes, there are, c'est infinite. And André, told, yes, but analytic is not possible. Okay, so this lemma is very useful in many circumstances. For example, it's one of the parts for getting vanishing cycle, which are the point for Novikov's theorem. And also, you can make a proof for proving that the lift of any Anosov flow has to be the universal there is R3, and you can conjugate on the lift to a constant vector field, your Anosov flow. And for that, you don't need to know anything in the topology on 3 manifold. You don't need to know any sophisticated things. And this theorem is not so sophisticated. It's not trivial, but it's not that difficult. Okay. So let's go to my mathematics now. One more. Okay, so here it's during his 90th birthday with someone here. And so Mehdi wrote me, I received a mail from Mehdi telling me that, oh yes, we are using, I like your work with André, and it's important for our work with Sam. And I say, okay, mend it to André, will be very happy. And unlikely, it was at precisely the moment where André was already at the hospital at the end. Okay. In fact, it's difficult to speak on André without to speak on his wife. She was a mathematician, but could not finish, for family reasons, the study. But she has an importance for all this community because of her kindness and also the, well, so I choose a picture with Minouche here. Okay. So let's go to my to foliation on the plane. So I guess that many people here know what are foliation, and also know that there are foliation on the plane are not only trivial one. But anyway, so there is foliation on the at the side. I also put the space of the leaves of the foliation. So if you have the space of the leaves is R, is because your foliation is trivial. But you know that there are some things that people call red component, but in fact this kind of picture, Poincaré knew that, so this picture has nothing to do with Reb, but it's some equivalent to the, it's used also by Reb for doing the Reb component. So now it's called also Reb components. And the interest of Reb component for foliation on the plane is that the two boundary leaves are not separated. Any neighborhood of one leaf contains leaves approaching the other side. So if you look at the space of the leaf space, you get a non-separated one manifold having one point on non-separation. And you can see that these two pictures are equivalent. You just open one for obtaining the other. You can get a little bit more complicated picture if you make infinitely many rate components. On that you can get easily by removing a point on R2 and taking universal cover. Then the space of leaves is at infinitely, so you have some branching here, but each point is only branch to one side. You have, at this level, each point is a branch with the guy at the right and the guy at the left, but then the other again and again and again. Okay? It starts to be a little bit complicated, but not so much. But now if you take, for example, some Weierstrass function for the top and also for the bottom here, so you have some disk bounded by two graphs, one having densely local minimum and here having densely local maximum. Each time you have, I'm not managing that very well, sorry. At each local minimum, you have that you have two leaves which are not separated. The same for the bottom. So at the end, you get some one manifold, so that the branching points are dense in your manifold. So, okay. If you have a foliation, then Poincaré-Bendixson implies that you cannot have any segment cutting twice, transverse segment cutting twice a leaf. So if you look at a transverse segment, all the leaves are cutting only one. That is, your segment represents all the leaves in an open set of your on the plane, meaning that the space of leaf is locally modeled by a segment. That is a one manifold. And we have seen that it can be not Hausdorff. The fact that it's simply connected is because R2 is simply connected. And there is a wonderful theorem of Kaplan that is clearly before the theory of foliation, but in some sense classifying the foliation on the plane, telling that, okay, you consider a foliation, and you say that two foliations are equivalent since they are conjugated by homomorphisms preserving the orientation of R2 and the orientation of the foliation, on the transverse orientation. Okay? And that is equivalent to oriented, simply connected, non-Hausdorff one manifold if you put some order on each branching. It's a one-to-one correspondence, and that side is up to orientation preserving homeomorphisms. Okay, let's start with understanding better this theorem. Okay, so we will make a proof. Recently with Theo Marti, we are doing a proof of the part that if you have a simply connected manifold, you can build a foliation having this simply connected manifold. And how we do that? The fact is that there exists a universal foliation on R2. And so let's see what is this universal foliation. You consider R2 with horizontal foliation, and then you will remove something which look like on some horizontal leaves, will look like a periodic Cantor set. You take a Cantor and you make it periodic, but according to you will do that in each horizontal leaf with vertical coordinate is rational, but according to the denominator, you start far and farther and farther. So, for instance, in some interval larger than the denominator. When you do like that, you get a closed subset of R2, meeting every rational horizontal lines. Okay, so you remove this closed subset, and you take the universal cover. And so that is a foliation. You can imagine it's a little bit complicated, but it contains all the possible complication. So we call that a universal foliation. I think that you should, at some moment it existed in math the word versal for telling, yes, it has some kind of universal property, but it's not unique. So if you want, we can cut the uni of universal. So the idea is that given any foliation, you just need to take this foliation and to consider some saturated open subset, and your foliation is equivalent to some saturated open subset of the universal foliation. And how you do that like that? So you notice that for this foliation, because on horizontal, on the rational horizontal leaves, you are removing something which look locally like a counter set. So this means that the connected component of the complement in that horizontal straight line, the connected components are ordered as the set Q. And if you take any totally ordered countable set as an ordered set, it is a subset of Q. So it contains all the possible ordered on countable subset. So now, if you consider some manifold with some branching, each branching you can see as a subset of the branching of this foliation. That is, you can include your manifold in the orbit space of that foliation. And now you consider this foliation, you consider the leaves corresponding to that embedding, and you get a foliated plane with the prescribed one-dimensional manifold, ordered manifold. So that shows you that you can realize every one-dimensional branch, non-Hausdorff manifold with any order on all the branching. And okay, this shows in particular that every foliation on the plane is obtained as a pullback of the horizontal foliation on the plane by some local homeomorphism or diffeomorphism. Okay, because certainly that is the case for this foliation, because it's a universal cover of so this foliation is a universal cover of the horizontal foliation on R2 minus this strange set. And so your foliation is some open subset in this universal cover, so it projects on the horizontal foliation on R2. Okay? Oh, sorry, I don't want to go. Okay. So now what the objective of my talk is to make the relation between the plane and the circle. So we will start with the easy part. That is, you start with the situation on the plane, and you want to induce something on the circle. And for that, you want to put a circle at infinity on your family of foliation. So it has been done in particular by John Mather in 82. And I remake some part, generalizing and also making some things more precise very recently. And so it's a very general setting. You take a countable family of foliation, and you need something like transversality, but individual leaf by leaf and only at infinity. So you don't ask to be transversal, you need just that. Given two leaves of foliations in your family, the intersection either is compact or the two leaves are equal. That's the assumption. And with that, you can build a compactification of R2, adding a circle at infinity. That is, you get a diffeomorphism of R2 in the interior of the disk, so that after passing through this diffeomorphism, any leaf go from one point to another point. But if you want uniqueness, you need to add something, because you could do that so that every leaf go to the same point, which would not be very fun. So we will forbid that the set of leaves arriving to a same point is more than countable. So we just ask that, given a point at infinity, the set of leaves arriving to that point is at most countable. And also, it would be easy it will not be unique if you allow that in some place on the circle there is nobody arriving. So we will ask that if you take some open interval, the set of leaves arriving there is, I put here, uncountable. That is because here I consider a countable set of foliation. But if you have a finite set of foliation, it's enough to have density. Okay, but anyway, we want that there are leaves arriving everywhere in the circle. We want that all the leaves are not, there is not all package of leaves arriving to the same point. Okay, and with that, there is a unique way of doing this compactification. The compactification is unique. And how you do such a compactification, so that the same idea as John Mather done, you notice that, okay, as the leaves are assumed that the two intersection is compact, so you forget the compact part, and you get that the end of leaves are disjoint rays. And you notice that on the plane, if you have disjoint rays, they are always cyclically ordered. And when you have a set which is cyclically ordered, you want to compare it as an ordered set with a circle. You cannot always make truly an embedding in the circle, in a strictly increasing in the circle. For that, you need to identify what has to be identified. Okay, you identify the two rays if on one side, two rays determine two intervals in the set in the cyclically ordered set of rays. And if one of these intervals is countable, you say these two rays has to be equivalent. You make the quotient of your set of rays by this equivalence relation, and now you can embed in R in S1 as a dense subset, and so you can complete this set as being a circle. So you get a circle associated to your family of foliation, and you put a natural topology on the union, telling that a neighborhood of a point at infinity is given by two rays arriving close to it on the circle, and you close by any segment, and you take this region that is an open set. So that's a very natural topology, and that makes that you get a disk with that. Sorry. Okay. The fact that the compactification is unique makes that if you have an homomorphism which preserves the foliation, then this homomorphism extends on the boundary of the disk, and so induce an homomorphism on the circle. And as that is completely canonical, you can also do that for a group action. If you have a group action on the plane preserving your family of foliation, then it will extend on the disk and so will induce an action on the circle. So I will call that the induced action. Okay. So now, in fact, we would like to go in the other direction, to start with the circle and to recover the plane. And so some question that I'm truly interested is to characterize the group actions on the circle so that they can extend on the disk, preserving either one foliation, maybe a singular foliation, or two foliations, certainly transverse, but maybe singular. This question, I have no answer for the moment, but we are working on it and we are very interested to, I think we can make progress, maybe not in the completely abstract way like that, but maybe for Anosov-like action. So for that, we think we have a path for answering the question in that setting. But let's show what question we answer indeed. We answer to, the first question is about transverse foliations, maybe singular, pair of foliations. So you take two subsets of pairs of points on the circle, and you ask yourself, is this subset are the pair of endpoints of the leaf of two transverse foliations? So this question is nice and we will answer it, but when you have a group action, building a complete set of pair of points on the circle look a little bit complicated, when it is maybe more easier to take just one orbit of pair of points. That is something maybe countable, and we would like to answer the question just using this pair of points, that is to use a countable data for that. And so for this reason that we are maybe more interested by the equation, you take two subsets of pair of points, and we would like to know under what condition you can complete that in two other, so larger pair of points, and these pair of points are induced by two transverse foliations. But we would like that the initial set of points correspond to a dense set of leaves of these foliations. So I will give a complete answer of these two questions. That is a preprint we have in archive with Thomas and Katie. Okay, and some maybe a little bit strange thing is that working with only one foliation is more difficult than working with two transverse foliation. And so I'm working with Theo Marti to answer to the question, but with only one foliation. Indeed, we have also a complete answer, but we have a complete answer which is only a draft of paper. It's written, but not yet a preprint. Okay. So let's start with the transverse pair of foliation. Okay, so we will work in what is called pre-lamination of the circle. Okay, so what is a pre-lamination of the circle? For that, you have to see that we distinguish, so there are, if you take two pairs of points on the circle, there are mostly three possible positions. Either they do not intersect, and if you take the geodesic or any continuous path joining them, you can choose they are related by disjoint segment, or they share an endpoint, or any continuous path going from one to the other has to cross. So let's say that is a non-crossing situation, and that is a crossing one. And a prelamination is just a set of pair of points which are just non-crossing, pairwise non-crossing. we use this terminology, the pre-lamination, because there is a terminology which is used that lamination has to be the same, but as a closed subset of pair of points. Okay. So we take two pre-lamination, L plus and L minus, and so for the leaf crossing, you just need that as sets of pair of points, there are disjoint. Because two geodesic either are equal or are transverse. So the word transverse is a very weak word, but if you want transverse foliation, it's clear that you need two more properties. You need that if you look at one of these pair of points and another of these pair of points, you can go from the one to the other by other pair of points crossing. So here you take a green crossing the red, then a black crossing the green, then a purple crossing the black, then a blue crossing, finally this dark blue here. So you can go from any two leaf by crossing leaves, by a finite path of crossing leaves. And you also need that on the circle, the endpoint, there is at least one point having one point of a pair in this interval. So we need density and connectedness. So is what we called to be fully transverse. We choose that name for these three properties: transversality, connectedness, and density. And so the answer, at what condition a pair of prelamination are in fact induced by two transverse singular foliation. So it's equivalent to be fully transverse, so the three properties we have seen. It's the fact that if you look at a point on the circle, you don't have three leaves arriving to the same point, but three leaves crossing a same leaf of the other foliation. And then we have two conditions. The two conditions is because we are looking at singular foliation here. So you look at a realization of your pair of points by segment on the disk or by geodesic for the Poincaré model, if you prefer. So you look at the complementary region of this realization, and you have two kinds of connected components of the complement. One is you get ideal polygons, but in that case, the ideal polygon has to be coupled. That is, you have one for one of the prelamination, and the other for the other, and you have each point of the same number of points for your polygon, and there are one in each component of the complement of the other. Okay. So that is one possibility. And the other, which is what's happened if you don't have singularity, is that when you look at the connected component, complementary region of your lamination, you look at the boundary component, and in fact, you need to have only one of these geodesic in the boundary, which is not a leaf, but it is just an accumulation of leaves, but it's not a leaf. All the others are leaves, and they cannot be all leaves. So there is only one on the boundary of this component, which is not a leaf. We call it the root of this component. And this root has something to do with the transverse lamination. Each leaf of the transverse lamination touching this component has to cross the root. So that is the hypothesis on the component which do not correspond to singular point. And with these two conditions, you have a unique foliation a unique pair of foliation, so inducing this pair of prelamination. And this pair of foliation is unique up to a unique conjugacy homomorphism, which is identity of the boundary. Let me explain a little bit that. So first, the easy thing is that, well, when you have coupled ideal polygon, you see clearly that it corresponds to a singular point. Okay? So one root region may be surprising you, but indeed, you have to see what's happened when you have non-separated leaves. When you have non-separated leaves, you have leaves accumulated to this set of leaves, but the endpoint of these leaves accumulated tends to the endpoint of the interval containing all the other. So these leaves, the endpoint go to there and there. So if now you forget the leaf and you just keep the endpoint, you get a sequence of segments accumulated the root. So that makes it very natural. And okay, how is the proof? The proof is in some sense very easy. You take a leaf of 1, and you look at the leaf AB, and you look at all the leaves crossing this one. They are naturally ordered because they are not crossing, they are pairwise non-crossing, so they are totally ordered. And the condition on the complement says that each time you have a connected component of the intersection, you have exactly one leaf, and the other is a whole, is an accumulation. And with that, you get that this set ordered naturally ordered, as an ordered set is like R, ordered naturally. And so you have the crossing to a segment is R. So now if you look at the leaf crossing between two leaves, it's a segment, and crossing the other direction is also a segment. So when you see this picture, the leaf, the intersection point inside are like a square. So you decide that that is the open set in the topology of the set of pair of crossing pair of points. So you look at two leaves crossing, you say that is a point. What is the topology in my set? The open set are union of rectangle, and you check that that is an Hausdorff topology. That makes that is a plane, and you have naturally the foliation, which are the horizontal and vertical foliation in the rectangles. So like that you get the proof of the theorem. Okay, and so as I told you already, we are interested in not considering all leaves, but just a subset of leaves. And for instance, countable prelamination, but maybe uncountable, but we would like to have not every leaf. Okay, and for that we also have a necessary and sufficient condition, and we also get uniqueness up to a unique conjugacy homomorphism, but the conditions are a little bit technical, and so I will not explain you the hypotheses. What I will do is make an example. So I will present you a setting where the statement is very simple. So I will consider specific prelamination that I call regular. Prelamination is regular if every leaf is accumulated on both sides. So you have a leaf which are two pair of points, and I ask that this pair of points is accumulated on both sides by pair of points. And we also want that there are no common points on the circle, so the leaves are disjoint. Well, I thought it was very natural, but my collaborators don't have that so natural, so I think why I have made this choice. And this choice is because is what happens if you take a foliation and you remove the non-separated leaves. If you remove the non-separated leaves, what you get is a regular lamination.
So can you repeat here what you want to, you say you want to prove something, an example.
Oh yes, I want to get exactly the same, make the statement of the theorem that I did not explain in that setting.
Yeah, exactly. I'm asking.
And so the theorem says that. The theorem says, take two regular prelaminations. They are, you can complete them so that the completed prelamination will be induced by foliation, and your initial prelamination correspond to dense family of leaves, if and only if they are fully transverse, because that is clearly necessary, and the unique condition you need is also very natural one. You don't see any polygons with more than 4 sides. If you have this condition, well, there is a unique foliation, unique up to unique conjugacy, so that your prelamination corresponds to a dense subset of leaves. Yep.
Can you remove the second condition if you ask for singular?
So no. No. If you put singular points, I have to explain the property of simple cycles. Okay. And the proof is a recipe for knowing what are the leaves that you need to add. And for that, the leaf you have to add certainly leaves on complementary region. So I'm considering a complementary region. And then I look at the other prelamination, and I built a graph, we built a graph for using the other lamination. The vertices of this graph are the boundary component of the of my complementary region. On the edges is if a leaf goes from one to another. So here, this red geodesic is a point of my graph. This also, and there is an edge because there is a leaf crossing both. The same from this on this, so there is an edge from it further, and so on. But for example, here there is no edges from here to there, and so on. As we're asking no polygons, we check that this graph, in fact, is a tree. And then, if you take any edge, we will find a new leaf to add as follows. You look at one of the vertices of this edge, and then you try to go the further possible by taking the other edges. So you go to there, and then you go to there. On the other side, you go to here and nothing else, because there is not. On the other side, you can go from here to there, and then to there, and from here to there. And we notice that because of the condition of the density, connectedness, and so on, there is on one side a unique point, on the other side a unique point, which makes the limit of these two regions that I just defined. And so I add the corresponding geodesic. So you add a leaf with this rule. So I make one, but we have to do for each edges. From time to time, the leaf we have to add are precisely a boundary component, but from time to time it is not. So you add these leaves. And now you look, once again, the new corresponding graph. Each time you add a leaf, what you do is you cut your tree, and you divide it in two connected components. And so, doing like that, at the end, what you get is just a tree with a unique root. And this root is not a leaf, which is precisely what was the condition for being induced by the foliation. So there are completions and so on. So that is the proof. Okay. So the fact that it is the uniqueness and the uniqueness of the conjugacy implies that if you have a diffeomorphism preserving my two pre-laminations, in fact, there is a unique homeomorphism on the disk preserving my two foliation on coinciding on the boundary with this one. And as this is unique, this allows to do that for group action. So if you have a group action preserving a pair of prelamination satisfying the hypothesis, then it extends as a group action on the disk preserving the two foliations. So that's okay. And so very quickly, I think it remains enough time for telling some words about the case with only one foliation. So I told you it's more difficult for one foliation, but indeed, Theo find a trick for using Kaplan's theorem so that the difficult part in the case of non-singular foliation, the difficult part is hidden in Kaplan's theorem. So it becomes easy in a non-singular part, and the difficult things are in the singular setting. But okay, let's start with a non-singular, trying to answer to the question, under what condition a prelamination is induced by a non-singular foliation? Okay. The first conditions are the same as previously, that is, we need a density of the point on the circle which belongs to a pair. We need that the set of leaves sharing the same point is at most countable. Okay? And we need this condition on the complementary region. That is, each complementary region admits a unique boundary component which is not a leaf but is accumulated by a leaf. And we call, once again, this the root of our component. But there is a new danger here, is that, you see, if I just here draw the geodesic, but you assume that the root, you have sequences of complementary region. Here there is one complementary region, one other, and so on. And they accumulated to some geodesic. But if you look at their root is here on the side, and the length of the root tends to 0 for the Euclidean matrix. So these roots are smaller and smaller segments. If you would like to transform that in foliation, this makes that this root correspond to leaves accumulated to the other. So these leaves are going from this interval, have to accumulate on the other side and go back. So they make an, I don't know, the coming and going back. And here also, and again and again. So if you take any transverse segment here, you will get tangency. So you cannot make a foliation like that. And so what we have to forbid is the bad accumulations. And this bad accumulation, you can see. Okay. If you look at the look the disk with the Euclidean matrix, so I will speak on volume. If you have 3 sides which are large, then the area of your component is large. As they are disjoint, there are finitely many components having 3 large sides. So as you cannot have 3 large sides, the 2 large are well defined. And so we need that up to finitely many components of diameter larger than delta, the root is one of the large sides. So that is our hypothesis. Okay? So here, for any complementary region with diameter larger than delta, we need that the root is one of the large side, and that is with the other hypothesis we already discussed, that is the necessary and sufficient condition for having a unique foliation, for having a so that this prelamination is induced by a foliation, and the foliation is unique. The difference is that the conjugacy homomorphism is no more unique, and that is a problem for group action. Okay? So what is the proof of that? Maybe better than not looking at... so that is a trick by Theo. He told me, yes, but that hypothesis makes that, given any leaf, if I look at a leaf crossing these, and I look the other one, they cut, the order is like R. So I get that the space of leaf of this prelamination is a one-dimensional manifold, maybe not Hausdorff, but simply connected. And we have seen with Kaplan's theorem, and also that for this reason that we remake the proof of the existence, that this one manifold corresponds to a foliation. And okay, the one manifold are also an order for the branching, but we can also realize the orders of the branching, so it corresponds to a foliation, and that is the proof. Okay? Okay, yes. So the non-uniqueness leads to difficulty. Yes, so here, sorry, it was not that. Okay. That was the case for, but I think it's time to end. So we have also, at what condition you can complete a prelamination so that it becomes a dense subset of leaf of a foliation. But this time, the completion is mostly never unique. So as the completion, you know, the completion is not unique because when you have complementary region, I told you the condition is the root has to be the one of the large side up to finitely many. So for finitely many, you can change the root. And also, you have 2 large sides, and you can choose the one that you want. And that is not, that gives different foliations. So you never have uniqueness of the completion, so the foliation here is not unique. But even in the case of you look at induced foliation, the fact that the homomorphism is not unique makes that if you look at if you consider a group action, you have not a canonical way to lift it, to lift the generators as homomorphism preserving the foliation, and so you don't get a group action of the same group. So for the moment, I'm not able to lift, to extend, to characterize the action on the circle that will extend preserving the foliation here. Okay, and so I just wanted to finish by 2 pictures of André, one with Minouche and Jean-Pierre Serre, and here in his garden, okay, recently.
Thank you, Kirsten. Questions?
So 2 quick questions. One is, Is there a Kaplan theorem for singular foliations of R2?
So
Or
that's
in
a
terms of R
difficult.
trees?
I presented only the non-singular part, but in fact Theo wrote the singular part. So there is a universal singular foliation, and that is much more difficult. So if you look at, you want to get a universal singular foliation so that the number of separatrices, I think is prong for people of Anosov community. So the number of separatrices is even. That is not so difficult. You take a subset like that, but you also add plenty of points, and you say, oh yes, on this point I will want a cyclic cover of order 3, 4, I don't know, well, everything. You have to choose every possible cyclic covers. So you can make a universal foliation like that for singularity with even number of separatrices. And for odd number, you have to cut it and to glue it back, which is a little bit more difficult, but it's done.
No, but what I was asking was, is there like a description in terms of you have a, I don't know, like a R tree with some order structure?
So yes, so the answer is, now, in that case, we will take the notion of leaf, also not the same as the community of Anosov, that is, we remove the singular point and we take the leaves in the complement. And so it's no more simple connected manifold, but you can characterize the condition. So you have a one manifold with non-simply connected, but with some properties. And you have the list of properties telling that are precisely the space of leaves, and they have to be cyclically ordered as the singular point, and so on. So there is a structure on a one-dimensional manifold which you say it's equivalent singular foliation of these one manifolds. But it has to be checked. Theo wrote it, and I have to check it.
Thank you. Thank you, Christian, for this talk and for speaking of André. I just wanted to add that the works of André that have been cited are just a small part, not a small part, just one chapter of the works of André on foliations, which is itself one part of the works of André in geometry and topology. Another important chapter of the works of André on foliations is what is sometimes called the homotopy theory of foliations, with the notion of Heffliger structure and the construction of the classifying space B gamma. André studied its connectivity and was part of the people who studied the characteristic classes of foliations. I just wanted to add this complement.
Any other questions? Okay, if not, let's thank Christine again.